Okay, so this is lecture 13 on the directional derivative and partial differentiation. A reminder that the page numbers I'm about to use are not quite matching your notes because it's a printout from a previous year. In your notes this semester in 2020, pages 149 to 157 give you the definitions and the basic examples, and then pages 158 to 162 discuss the idea of continuous differentiability, and that is a nice condition for making a connection between the directional derivative and the partial derivatives through something called the gradient. So that's where we're going. The most important and takeaway formulas are at the end of this lecture, but every bit of it matters. Okay, so let's just get into it. So the start of my chapter 4, as is usually the case, gives you a big picture synopsis of the whole chapter. And basically what I say here is that differentiation is about capturing the best linear approximation to the change in a function at a point. And in order to do that, we need something called the general derivative. This general derivative is going to be essentially built, the pieces of it are going to be built from partial derivatives. And partial derivatives are understood in terms of directional derivatives. So that's why we're going to start with directional derivatives, with our ultimate goal in mind being constructing a linearization for a function that gives us the best linear approximation to a function. That's our ultimate goal with this material. But of course also partial derivatives are used throughout science and mathematics, so we'd like to understand how to calculate those. And the good news is it's pretty easy. In fact, if I don't really care about all the theory here, and if I just want to teach the mechanics of partial differentiation, I think I could easily do it in about 20 minutes for students who know calculus. So the basic idea here is for directional derivative is to take a function of two variables. We're going to start with a function of two variables and fix a point in the plane, x0, y0, and we're going to try to understand how the function changes at that point in a given direction. And so let me just scroll up here a bit. So see here, this is a parameterization in the domain that goes in the direction AB, and it has base point x0, y0. So we're going to study the change of the function at the point x0, y0 in the AB direction. And for the sake of specificity, we insist that the vector AB be a unit vector. So in this picture down here, which I think you can see, I pictured in the plane the line parameterized by r of t. It's down here. See that little orange line? So it goes through the point x0, y0. It has direction vector u. This u hat, is my notation for a comma b. All right, that little green vector down there. And so if I think about the graph of f of xy, it's like z equals f of xy. That's what I have, this shaded region right there. All right, it's like this shaded region is the graph z equals to f of xy, where f of xy is the function we're trying to study the change in, right? And so this up here, gamma of t equals to x0 plus ta, y0 plus tb, and then f of x0 ta plus y0 tb is that blue line. That's a parameterization of the blue line. So basically we're using the x and y for that path, and we're just writing along the z, evaluating f there. So that, if you think about it, is going to tell us how to understand the change in the function in that direction, right? Because if we take this vertical plane, we draw it over here, there's that blue curve written over here like that. The unit vector AB actually lies in this vertical slice, and the intersection of the graph with the vertical plane is the blue line, and so the tangent vector to that that curve, right, would be v, and you can see that that tangent vector must lie in the vertical plane because of the geometry here, And furthermore, if we look at the change in t along the curve versus so like basically we can think about this vertical slice having the z-axis and the t-axis as it happens, because it's a unit vector, so it really is a t-coordinate along that orange line if you think of it that way. And anyway, so basically we can calculate the change in the function with respect to time, and that's going to capture the change in the function in the z direction. Excuse me, the change of the function in the u direction at the point x naught y naught will be delta z over delta t. And so that's what I'm trying to motivate here with this picture, is that what we have actually is that the value of the derivative, so like the z component of this tangent vector, right, which is going to be like ddt of that, right, ddt of that should give me the z component of the tangent vector to the curve. And that should describe the change of f of xy in the direction AB at the point x naught y naught. And for that reason, we define the directional derivative of a function at a point x naught y naught in the u hat AB, that has to be a unit vector, direction, as follows. We just take the limit as t goes to 0 of f of p naught plus tu minus f of p naught divided by t, which you can write also in terms of, since it's two dimensions, this breaks down to f of x naught plus ta, comma y naught plus tb minus f of x naught y naught divided by t. This notation right here, incidentally, is how you would do it if your function was a function of like 3 or 4 or how many variables. This formula would still make sense. So like the reason I'm writing this here is just to point out that if you think about it in terms of vectors, it looks like this. Here's how it breaks down in terms of components. But actually, already we're seeing the formula which works in 3 and 4 and however many dimensions you like. Okay, so let's look at an actual calculation of one, right? Oh, I guess I should say, by the way, that definition, if you look at what we had a difference quotient, and really we're taking the derivative with respect to time of the function evaluated at that line in the AB direction at x naught y naught. And after we're done with it, we're evaluating t equal to 0. Okay, so here's like a straight up example. And as is usually the case in math, we show you the wrong way to calculate examples to start with, just to illustrate the definition. Like this is not the way we'll be doing it after the dust settles here, right? But so we take a point, x naught y naught, and take a unit vector, 3, 4. Actually, 3, 4 is not a unit vector, so I have to divide by 5 to make it a unit vector. And so I need a function. Oh, there's my function. I've failed to read my problem. F of xy is 25xy, right there. And so I want to calculate the rate of change of f at the point 1, 2 in the 3, 4 direction. So basically, first of all, I have to make that 3, 4 vector into a unit vector. I do that. And then what I'm doing is I'm evaluating the function at the path centered at p naught in the u hat direction. And when I do that composition, 25 times x times y, that's the x, that's the y, 25 times that, and multiplying it out, I get this expression here. And then what I have to do is I have to differentiate that, like so, and then plug t equal to 0. I do that, I get 30 plus 20, which is 50. So the rate of change of 25xy at the point in question is 50. Now, of course, you could also take the limits explicitly if that makes you feel better, but I personally prefer to rely on calculus that you guys already know, because it's like way faster than calculating difference quotients. Anyway, so then you guys are not math majors, right? So probably calculating limits explicitly is not going to give you joy. And that's okay. So same function, but this time we're going to calculate the rate of change of f at the point 1, 2 in the direction of 1, 0 or 0, 1. Of course, you should recognize this as x hat or y hat, right? So here we go. So we look at the function at the curve 1 plus t comma 2, because that's, the curve in the direction of x hat centered at 1, 2. and plug that in 25xy, which is 50 plus 50t, and differentiate that, and plug in 0, we get 50. All right, and then in the y hat direction, right, we get plug in p naught t y hat, which is 1 comma 2 plus t. Notice the difference. So the x derivative had 1 plus t2. This one has 1 comma 2 plus t. So like that gives me 25 times 1 times 2 plus t, which is 50 plus 25t. And when you differentiate that thing, you get 25. So notice that this shows you that our direct calculation that we did to start with in the previous example, we got 20 plus 30, which was 50 for that directional derivative, right? And so we could see that linking these two examples, 50 is 3/5 50 plus 4/5 25, right? Because that's 30 plus 20, which is what we had before, 30 plus 20. And so there's a relation, apparently, that the directional derivative in the u-hat direction is given by the 3/5 dx hat, 3/5 times the partial derivative in the x hat direction, plus 4/5 times the derivative in the y hat direction. And to be more clear, like the pattern that we're seeing is, in fact, that the directional derivative is the unit vector dotted with this vector made of directional derivatives. In fact, this has a name. This is, later we'll call this the gradient of f. This is, by the end of today's talk here, we'll get to the point of realizing that that's a comma b dotted with the gradient of f evaluated at the point p naught, all right? But there is a comment from the future. If you don't understand that right now, you shouldn't, but if you watch this a second time, that'll make sense, all right? Not saying you have to watch it twice, I'm just saying that comment will make sense later. So in short, the directional derivative in general, we just take the function we're interested in, we evaluate it at a line which is centered at the point we're calculating the directional derivative with a direction vector and a unit vector pointing in the direction we're calculating the change with respect to. And so that's how you calculate a directional derivative. All right, so that said, the way to calculate directional derivatives is not from the definition. It's actually from the use of partial derivatives. And so for that reason, we're going to calculate a bunch of partial derivatives here to get better at that before we do any more directional derivatives. So what's a partial derivative? So the partial derivative of a function of two variables with respect to x at the point x naught y naught is nothing more than the directional derivative of f at the point x naught y naught. And the partial derivative with respect to y, so these are not, this is the partial symbol, that's a partial symbol. You haven't written these before probably, okay, it's a new symbol. It's not d, like df dx has a different meaning. You shouldn't write df dx, you must write partial f. Partial x indicates a partial derivative. And what that really means notationally is that there's more than one independent variable in the domain of the function in question. So that notation alerts the reader to the fact that the function you're dealing with has more than one moving part, all right, so to speak. And anyway, these symbols are funny because maybe you haven't seen them before, right? So partial f partial y at x naught y naught is the directional derivative of f in the y hat direction at the point x naught y naught. And again, of course, this is provided that those exist. These are the so-called partial derivatives. And so great. Well, I can write. Let me take a second here to write them out explicitly in terms of the limits for just a second. So I already did some of the work beforehand. So here's some notation like fx x naught y naught is another notation we have for partial derivative. And so partial f partial x x naught y naught. What that is we take the limit, and so the way it works is basically we take and we let the x component vary, and we leave the y component alone. And I see I have not written small enough. So this is minus, and what's supposed to go right there, but I have poorly planned with my marker, is x naught, y naught. I'll do better down here. F of x naught comma y naught plus h. I should have used a pen. Oh well. F of x naught y naught. Sorry, poor planning on my part. So basically you take the difference quotient fixing y, or you take the difference quotient with like x fixed at x naught. So if you look at it, what we're really doing is we're differentiating with respect to time the function f of t comma y naught. And once we're done with that differentiation, we're setting t equal to x naught. This one, we are differentiating the function with x fixed and letting the y vary. Differentiating with respect to y, basically holding x naught fixed, x fixed at x naught. And after that's done, we're setting t equal to y naught. So, I mean, anyway, this is sort of a quick explanation for how you calculate these, but I think it'll be better if I show you some examples. Before I do a little bit more notation, we can also talk about like second partial derivatives, so like fxy, and this is the y partial derivative of the x partial derivative. And so like yet another notation for that would be partial y of partial xf. And fun theorem for nice functions, we can commute the partials like that. And so like f of xy is equal to f of yx. And this is sometimes called Fubini's theorem. All right, now I'm getting out of order here, so I'm gonna get back on track here and show you some examples. But first, I should tell you more about the geometric meaning. What is the geometric meaning of the partial derivatives? I mean, it should already be implicitly understood because we have defined partial derivatives in terms of directional derivatives. And so, right here's, oh, and I suppose you remember in Calculus 1, once we differentiate a point, it allows us to define a new function called the derivative function. Well, that same thing is true here. Because we can differentiate at a bunch of points, we can think about making new functions of two variables called the x partial derivative function and the y partial derivative function, right? Or second partials with respect to one variable or with respect to both. You know, there's anyway, these are all new functions that we can build from the given function f, provided that these partial derivatives exist, all right? So anyway, in short, the real thing that we need to make sure we understand is that f sub x, and again, f sub x is just another notation for partial f partial x, right? Like I say right here. This gives us the rate of change of f in the x direction. Fy gives us the rate of change of f in the y direction. And of course, the rates of change are different at different points. If you want to find out the rate of change at a given point, you plug that point into the x partial derivative to find the change at the function in the x direction at that point, and same for y. All right. And again, these are the formulas I just wrote down a second ago on the other paper. All right, so, and here's a picture, actually, I was telling you. Here's a picture of the geometry, if you will, of the partial derivatives. So you can understand it if you think about the graph of the function, which I've made this picture of, and if you think about lines that sort of trace out a vertical slice that is either parallel to the y-axis, or a vertical slice which is parallel to the x-axis, right? Which I've made these dotted little plane slices to indicate. So like where that graph intersects this xz kind of vertical slice, that I've pictured over here as that blue curve, and so like the slope of that is going to be related to partial f partial x, because that tells you how the function's changing in the x direction at that point. And likewise, if we look at that vertical slice, we can look at the tangent line there, and the slope of that one is going to be partial f partial y, which again tells us how the function's changing in the y direction, right? And we can think about those actually in terms of, actually taking the velocity vectors of these particular curves, which trace out those lines along the surface of the function. Okay, well, great. So I include this discussion because students always ask, oh yes, but what does this mean? What does the partial derivative mean? Well, this is what it means geometrically. What properties does the partial derivative have? Well, I just explained to you that the partial derivative is defined in terms of the derivative from calculus 1 with a little window dressing, basically. And so what it means then is that all of our favorite properties of differentiation are still true for partial derivatives. Like 1 and 2 are linearity of the derivative. We can break up sums. We can pull out constants. We have a product rule for the x derivative and the y derivative. If we have a composite of a function on the reals with a function of two variables, then we have this chain rule that we do derivative of the function of, like basically dh dt is just like a calc 1 derivative, and we have to evaluate that at the multivariate function, and then we multiply by partial f partial x if we're taking a partial x derivative. A quick notation for this is just dh df times partial f partial x. This notation, dh df, means we're differentiating the h function and evaluating at f. It's like a slick notation for that. And likewise over here, if we're partial differentiating with respect to y, we have this chain rule. Finally, point 5, we have that, the function x and y themselves are functions. And just to point out, what do I mean by that? I mean, the function x is defined as follows: f of xy equal to x. Okay? The function y is defined by f of xy equal to y. I mean, this is the x function, this is the y function, so you can calculate the partial derivative of that function. And when you do, you find the somewhat, I think, comforting results. Partial x is 1, partial x partial y is 0, partial y partial x is 0, and partial y is 1. And I often put the proof of these on the test, right? Now, the only way I can put a proof of these on the test is if I don't give you a formula sheet, unfortunately. So you think about your life. What kind of test do you want to have? Do you want to have a test with a formula sheet or without a formula sheet next time? I'll let you guys. I'll put you guys in the driver's seat for that. Let you decide, maybe. But anyway, here's the proof of the chain rule. So basically, partial x says I take the function in question, I vary the x component but not the y component, and I differentiate. So by the rules of calculus 1 and the ordinary chain rule, I get this. And then when I plug in t equal to 0, I get exactly dh dt at f of xy, and this, when I evaluated 0, is partial f partial x. So basically, the chain rule that I advertised in the in the above proposition, it follows immediately from the ordinary chain rule in calculus 1. And the proof that partial f partial x is 1 is right here. It's just this. So, but sometimes another useful comment is part 5 here actually shows you that the variables x and y are independent. Two variables could be taken to, a definition for variables being independent could be that partial derivatives of one variable with respect to the other are 0. If that's the case, then without strings attached, I'll say, then that makes the variables independent. Okay, great. And here's the rest of the proofs I'll skip. Let's get into the examples. You're like, good grief, we're 24 minutes into this video, you still haven't done an honest to goodness example. Yeah, that's true, but we have to go through these definitions, otherwise it's just not right. Let's see here. So here's the partial derivative of 2 to the x squared plus y squared. So the way this works is we do the derivative of the 2 to the something function, which is log 2 times 2 to that something, and then we do partial derivative of the inside function. So I'm using the chain rule from the proposition I just mentioned. Now the partial derivative of x squared plus y squared is the partial derivative of x squared plus the partial derivative of y squared. And so we get 2x partial x and 2y partial x. Of course partial x is 1 and partial x is 0. So that just gives us 2x, which I have written as 2 log 2x x to the x squared plus y squared. Now, I don't usually write these details all out when I do a partial derivative, but I'm doing it to start with because I want you to understand the logic here. So here's another one, partial derivative of sine of x squared y. So chain rule says that it's cosine of x squared y times the partial derivative of the inside function. Y is constant with respect to this partial derivative, so we can pull it out essentially. But I'm just doing the product rule because I'm being methodical at the moment. So we pull y out because it's this is just the product rule. And this piece is 0 because partial x is 0. And the x derivative of x squared is 2x partial x, which just gives us 2xy. So there you go, 2xy cosine of x squared y squared. So I've included some extra steps in these examples I will soon stop doing. I just wanted to show you, like some gory details here. So here's like a quicker calculation, I suppose. Derivative with respect to y of sine x squared y. So I do cosine of x squared y times, partial derivative of x squared y. What's the partial derivative of x squared y with respect to y? Well, it's just x squared. So the thing that's driving that is that partial y of x squared y. Basically, x squared is constant. You can pull it out. That's how I think about these. When we're partial differentiating with respect to y, the x is a constant, so you can pull it out. And then partial y is just 1, so we just get x squared. So the chain rule and this calculation give you that answer right there. All right. This always kind of gets students a little bit because you got to think about the difference between two kinds of functions, like x to the y versus y to the x. Well, notice here I'm differentiating with respect to x and differentiating with respect to y. So we get the usual power rule. We lower the power by 1 and we multiply by the power originally, right? In contrast, here I'm differentiating with respect to the exponent. This is an exponential function with base x, so I get log x to the y. And the second one, this is an exponential function with base y, if I think of x as the variable holding y fixed. So I've got log y times y to the x. So there's some examples for you. Here's a more grievous example, x to the y squared, which would be, let's see here, so I do y squared x to the y squared minus 1. All right, and on the other hand, if I have the y derivative of that, well, then I've got a chain rule to think about because here this is an exponential function, right? Now if I wrote it in a different sort of notation, this is like the exponential function a to the t squared, right? If you do ddt of a to the t squared, the way that works is the natural log of a times a to the t squared ddt of t squared, right? Well, maybe you forgot, but there it is. And so here the t is like the y, and that's why I end up with 2y natural log of x x to the y squared. So this is the calculus 1 behind that calculation right there. All right, well, moving along. I have a stupid number of examples. I hope you don't mind if I kind of go through them all. Again, if you're you're bored of me talking through these examples, you may skip ahead. There's a lot of them. So partial derivative with respect to x of sine of x squared y cos x. Again, when we differentiate with respect to x, we think of y as a constant, all right? So first of all, I've got the chain rule because the sine differentiates to cosine, and then I have to do the derivative of the inside function, which here is x squared y cos x. And so how do you differentiate x squared y cos x? I claim that you get 2xy cos x plus x squared y sin x. And so, what do I say? I say, can I skip the middle step above? I say some days yes, some days not. Should you? Probably not. So, in other words, I'm inviting people who read my notes to actually work that out. That's what that comment means. And I'll work it out for you right here. Partial x of x squared y cos x. So what we got is partial x of x squared times y cos x plus x squared partial x of y cos x. Now this y we can pull out front. Let's just pull both y's out. And then we're going to get 2x cos x from the first one, and then over here we get plus x squared partial x of cos x. I didn't do the differentiation yet. Cos x is the hyperbolic cosine. You may or may not have seen that before. I'm not sure if you guys have that in your curriculum or not. If you don't, it's unfortunate. Everybody should know about hyperbolic sine and cosine. So this is 2xy cos x plus x squared y, I'm multiplying that back through, sin x. Okay, fine, obligatory crash course in the hyperbolic sine and cosine. So if you already know hyperbolic sine and cosine, you can skip ahead a minute, but basically if you take e to the x and you write it as 1/2 e to the x plus e to the minus x plus 1/2 e to the x plus e to the minus x. That was a mistake, I made a minus there. Notice I'm just adding and subtracting e to the minus x over 2. Then you can prove that this is an even function. You can prove that this is an odd function. And in fact, cos x is that even function. It's 1/2 e to the x plus e to the minus x. And sin x is 1/2 e to the x minus e to the minus x. From those, it's immediately easy to see cos of 0 is 1, sin of 0 is 0, and other things like the derivative with respect to x of cos x is what? It's sin x. And also the derivative with respect to x of sin x is cos x. And there's more. Fundamental identities for cos and sin. You can try this out. So 1 equals e to the x times e to the minus x, right? And so that's cos x plus sin x. And think about it, since sin is odd, we can write e to the minus x as cos x minus sin x. Again, using that sin is odd and cos is even. And so that gives us cos squared x minus sin squared x because the cross terms cancel. And so I call this the Pythagorean idea, Pythagorean identity for cos and sin. Other people have disagreed with my usage. In fact, I had a paper where I wrote that, and the reviewer was like, "Arr!" But anyway, they're dumb. So whatever. So here's hyperbolic sine and cosine. They come up in all kinds of applications all over the place, and I'll shut up about that now since it's kind of off topic. All right, back to the differentiation. All right, back to the differentiation. Here we go. So here is an example. Oh, goodness gracious. I'm going to get tired of my examples here pretty soon. Derivative of sine of cosine of the square root of xy. So we do cosine of cosine root xy times the partial derivative of y with respect to cosine xy, because we're, chain rule again, derivative of sine is cosine, cosine of the inside function, then differentiate the inside function with respect to y, and so that gives me a minus sine xy, then I differentiate the inside function, which this time is square root of xy, and then that gives me 1 over 2 square root of xy times the partial derivative of xy with respect to y, which just gives me x again. And yeah, there you have it. And of course I've done some algebra to be annoying. So what I just did, good grief, why did I do that? Just to confuse students, I guess. All right, partial xy of xy is x times partial y. We pull the x out. And so that's just x. And so basically you've got x over the square root of xy, which you could rewrite as the square root of x squared over xy, assuming x and y are positive. We are assuming x and y are positive here. All right. And so that's the square root of x over y, which is what I have written over here. So that's the mystery of that expression there, okay? Next I have x squared plus y squared. Why didn't I start with this example? That would have been so much easier. I always do this. I have the easiest examples at the end. Partial x of x squared plus y squared is just 2x. With respect to y, you get 2y. And here's another example. We have x e to the xy. With respect to x, we face a product of functions of x. We have to use the product rule, and that gives us that. On the other hand, when we differentiate with respect to y, we don't need the product rule because there's only one function of y. We can pull that x out because it's constant with respect to y derivative. And then, well, chain rule says we have to differentiate the inside function again, and so we get that. All right, I'm going to go ahead. Here's some second partial derivatives. If we have xy squared, we can calculate fxx. It's partial x of xy squared. So that first one gives me y squared, and when we partially differentiate y squared with respect to x, we get 0 because y is constant with respect to the x partial derivative. And when we do xy, we get partial y of partial x of xy squared, which is just y squared, and then partial y of y squared is 2y. Great. And the cool thing is if we do the differentiation in the other order, xy, like this, then, and this is not a typo, guys, like fyx, what that means is fyx. So if you write that in operational notation, it puts the x first, because that parentheses x means partial x of fy. Just that's not a typo, okay? But anyway, partial y of xy squared is, well, I can pull, basically the x comes out and I get 2y, so I get 2xy. Then I differentiate this with respect to x and I get 2y. I get 2y either way, so that's an example of that Fubini theorem I mentioned earlier, that you can commute the partial derivatives. For nice enough functions, you can come up with pathological examples where the partial derivatives exist but are not equal, but man, they're kind of hard to come up with. So there's some second partial derivatives. Here's some second partial derivatives. Third partial derivatives in a function of x and t. So if we can play this game with respect to x and y, we can play it with respect to other letters. All right, that's what this example's about. And here's a derivative with respect to t and then x and then x. This is a good example. This does something we haven't done yet in any of the other examples, which is calculate a partial derivative and then evaluate. So here I say find fx 3, 4. What that means is you calculate the partial derivative of that function with respect to x, and then you plug in 3, 4. So I start by calculating the partial derivative at an arbitrary point, which by the chain rule for natural log gives me 1 over the argument times the derivative of the inside function, which gives me this unpleasant expression. And then since I'm calculating that partial derivative at 3, 4, I plug in 3 and 4 into that. So like 3 squared plus 4 squared is 25. Square root of 25 is 5. So that's like 3 plus 5, which is 8. And so this is 1/8. And this is, on the other hand, 1 plus 3/5. 1 plus 3/5 is, I think, 8/5. So the 8's cancel. The 1/8 times 8/5 times 1. 8/5 times 1/8 gives you 1/5, which is how that happens. If you're confused about where the 1/5 comes from, just plug the numbers in here and you'll see it. Here's another example, and example with partial derivatives with respect to S and T. I'll let you look at these. We can also revisit fundamental theorem of calculus part 1. It's still true in partial derivatives, appropriately understood. There's some examples of that. All right. I don't know about you, I'm getting tired of my examples. And here's partial differentiation where the variable is, it's not just x, it's like sine of x or x squared. That means you got to do the chain rule. And then even here down here is some partial derivatives with respect to alpha and beta. If you've got a function of alpha and beta, then we can think of alpha and beta as independent variables, which means that when we're differentiating with respect to alpha, we treat beta as constant, so like cosine beta just comes out, and we get derivative of sine alpha, which is cosine alpha. And likewise for the other one, with the beta derivative, the alpha is constant, so we just pull it out. Yeah. And here's all the derivatives of y tangent 2x up to second order. So I calculate the x derivative, the y derivative, the zxx, the zyy, and the zxy. There they are, all of them, in gory detail. Okay, now, so finally, at the end of my examples, let's talk about directional derivatives and the gradient. So, a long time ago, in a land about 30 minutes ago, 20 minutes ago, we came to an example where we noticed that this pattern was true, that the directional derivative of a function at a point in the AB direction was given by the dot product of like the x derivative and the y derivative with AB. Now at that time we were calling it directional derivative in x hat direction of f at the point x naught y naught, right? And directional derivative in the y hat direction of f at the point, goodness gracious, x naught y naught. But that's just a really, really ugly notation for the same thing, right? Because this and that are the same thing. Partial derivatives are directional derivatives in the coordinate directions. So you might wonder, is this generally true? Is it always the case that you can build the directional derivative in the AB direction as a dot product of, like, can you build it from the partial derivatives dot product with a unit vector and you're interested in the direction of? Can you always do that? Well, since I'm asking the question, the answer is no. So here's an example of how it can break down. You define the function, which is kind of a funny function, but x plus 1 when y equal to 0, y plus 1 when x is equal to 0, and 0 elsewise. I mean, 0 otherwise. And so like you can calculate partial derivative at 0, 0 in the x direction, or partial derivative with respect to y at 0, 0, and you get 1 for both of these. And yet the directional derivative, if you go in any other direction than 1, 0 or 0, 1, you get this, which is, well, these are strictly 0, because we've defined the function to be 0 except on the coordinate directions. And if a and b is not a unit vector in the coordinate directions, then this puts us at one of the points out there, so that's just 0. And f of 0, 0 by definition is 1, so that gives you minus 1. And limit t goes to 0 of minus 1 over t, well that doesn't exist, right? That's infinity and minus infinity. And yet the directional derivatives are 1 and 1, so it would seem like it might work, but it doesn't. The directional derivative never exists, so you can't very well build it from partial derivatives which do exist. So what I say is the directional derivative in any non-coordinate direction does not exist since the function jumps from 1 to 0 along the any line except the axes. Now, you could come up with a less extravagant example to prove that same thing. Like you could just make a function which is 1 on x axis, 1 on the y axis, and it's 0 otherwise. And in that case, the partial derivatives both exist and they're 0, and the directional derivatives fail to exist for pretty much the same reasons as the last example. So the function looks like this, right? So like, yeah, the function, if we just focus our attention along the axis, well, yeah, the partial derivative exists, right? But it doesn't really make sense to talk about a derivative in other directions because it's not continuous, right? It's not even continuous there. The function's not even continuous there. Now it turns out that if you insist that the derivatives as functions are continuous, then that fixes things. So a function is said to be continuously differentiable at a point if the partial derivative functions are continuous at the point. And so we'll say f is an element of C1. That means that the first derivative exists and it's continuous. And if all the second order partial derivatives are continuous, then we say it's a C2 function. If continuous partial derivatives of arbitrary order exist, then we say the function's smooth. And f is in C infinity at the point. So we'd like to work with smooth function because we don't really want to worry about our partial derivatives not existing past some order. But I will say, in financial mathematics, people study more interesting functions which don't behave like that because, for example, like stock market price or something, it's far from continuous. It's some kind of like infinitely jagged thing, So this classical continuous calculus maybe is not the right tool set for your financial problems that you might be interested in. You might need to learn something called stochastic calculus, which I know less about. But that might be a good topic for your analysis class. Just thinking. Hey, you guys need to pick topics. All right. Anyway, getting back on track here. So this is the proposition: any directional derivative of a function at a point in the AB direction, we can just build from the dot product of the partial derivatives evaluated at the point with the unit vector, assuming that f is continuously differentiable. Now, I'm not going to prove that right now. We'll delay that till later. And it's also convenient right now to introduce a notation for the vector of partial derivatives that we just stumbled across. And so the gradient vector is what we get when we take x derivative and y derivative, pair them together as a vector, or x hat partial f partial x plus y hat partial f partial y. This is also denoted grad f for gradient in some books. Right, and this is the gradient of f. The upside down triangle is also known as nabla, and you can think about nabla as that operator, a vector operator, x hat partial x plus y hat partial y. That gets some mileage as an idea. There's a certain beauty of thinking of it that way, but anyway, so the proposition written in the gradient notation is just this: the directional derivative at the point x naught y naught in the AB direction is given by the gradient evaluated x naught y dot with AB. This is how I think about calculating directional derivatives. I use this formula. This is the way to do it. Because that formula immediately reveals things to you that you can, well, just think about it for a second. If this is a unit vector, right, and that's a unit vector, right, so we could also use the formula for dot product. This is the length of the gradient of f at the point times the, cosine of the angle between them, right? Where here I'm saying that the gradient vector points like this, and AB points like that, and here's theta. So I mean, once you make that leap, because we know dot products, and we know how they relate to the cosine of the angle between the vectors, and so I mean, for example, if the direction vector is perpendicular to the gradient vector, the rate of change is 0. If the direction vector is parallel to the unit vector, parallel to the gradient vector, that means that the rate of change is as big as it can be. It's maximized, and the length of the gradient vector is that maximum rate of change. If they're anti-parallel, in other words, if theta is pi or 180 degrees, if you like, then the rate of change is as large and as negative as it can be. This completely captures what the possible change is for the function in different directions, because we know how dot products work and we understand this formula. Now that's what I'm going to say in the next 2 pages of the notes, basically. But I thought I should say it for you now, here, so I did. Here's an example, just to bring it back down to earth here for a second. X squared plus y squared, the gradient of f is, partial x derivative of f, comma the y derivative of f, which is 2x 2y. And so if we wanted to calculate the derivative of, directional derivative of f in the AB direction at the point x naught y naught, we take this gradient, we evaluate it x naught y naught. When we take the dot product with AB, we get that formula. There it is. All right, so as I was saying, it's often useful to write the directional derivative in terms of the magnitude of the gradient times the cosine of the angle between the gradient and the direction in question. Because once we do that, as I was just arguing, the following proposition should be clear. In particular, if we want maximum increase, we look at theta equals to 0, which is to say that AB points in the direction of the gradient. Professor I used to teach with used to say that the gradient vector was like a compass to take you up a hill. If you think about f as being like height, always follow the gradient vector to take you up the hill. I like to say that if you follow the gradient vector, it lets you level up. So, on the other hand, if you go opposite direction to the gradient, then you're going to level down as fast as possible. You're going to decrease f as much as you can. If you go parallel, if you go perpendicular to the gradient vector, you're going to make the change in the function 0, which is to say that you're going along a direction where this function stays constant. Okay? These 3 principles are going to help us to understand the geometry of level curves in a future lecture. Okay? So like x squared plus y squared, in which directions is this function increasing the most at 2, 3, decreasing the most at 2, 3, and not increasing at 2, 3, right? So theta equals to 0, theta equals to 180, theta equals to 90, right? Essentially. But we got to think about like plus or minus directions too. So when we calculate the gradient, we get 4, 6 at that 0.23. And so make that into a unit vector. We get 1 over root 13, 2, 3. And so anyway, the magnitude of the gradient vector is root 13. So that is the maximum rate of change, and it happens in the, you could say 2, 3 direction, or unit vector 1 over root 13, 2, 3 direction. Decreases in minus that direction, and the maximum rate of decrease is minus 13, or you could say the rate of decrease is 13 in magnitude. And if you want it to be constant, well, you just want to be perpendicular to 2, 3, right? What vectors are perpendicular to 2, 3? They're the ones that satisfy 4a plus 6b equal to 0, and we need a unit vector, so we need a squared plus b squared equal to 1. And so like, you could think about that sort of geometrically. A squared plus b squared is a circle. That is, b is equal to, minus 4a over 6. So if you're thinking about the, like AB plane, think about A and B kind of like x and y. A little bit AB plane, well, that's a line with slope minus 2/3, I don't know what that is, something like this, right? So there's going to be 2 points on the circle, which this line and the circles both solve. And this algebra shows you that the points are given by A is plus or minus 3 over root 13, and B is minus plus. The minus goes to the plus goes to the minus, like that. 2 over root 13. So that's this point and that point, which correspond to these unit vector directions. F is constant in either one of those directions. So that's a pretty standard test question for me. I give you a function, And then I ask, find the maximum rate of change, the minimum rate of change, and also describe a direction in which the function's constant. So here I ask to find the point at which the function x squared plus y squared is constant in all directions. Right? For it to be constant in all directions, that would mean that the directional derivative is 0 in all directions. The way that can happen is for the gradient to be 0. And so that happens for this function when we plug in 0, 0. Great. And that leads me to a definition, which is that if the gradient vector is 0 for a function at a point, or if it doesn't exist, then that's said to be a critical point of the function. All right, we'll need that definition. We'll need that. It's going to be, to make a horrible pun, mission critical to understanding optimization later in this course. And finally, here's just some garden variety directional derivatives with the right kind of idea. We've got f as y squared over x, and we're going to look at the point 1, 2, calculate the rate of change of f in the 2 root 5 direction. All right, so the length of 2 root 5 is actually 3. So we have to normalize by dividing by 3. That gives us a unit vector. Always remember this, to calculate directional derivative, you need a unit vector. And so then I calculate the gradient to that function, which is minus y over x squared and 2y over x. And I plug in the point 1, 2. So I put x equal to 1, and I put y equal to 2. That gives me minus 4. That gives me 2 times 2 over 1, which is 4. This is u hat, and I take that dot product. I get 4 root 5 minus 8 over 3. And there it is. That is the rate of change of this function at the point in that direction. So that's how you do it. Calculate the gradient, plug in the point in question, and take the dot product with the unit vector in the direction in question. That gives you the rate of change. Simple as that. Simple as that. Here's another one. Here's a function. I calculate the gradient at an arbitrary point. I plug in the point 4, 1. That gives me the gradient vector. I take the dot product with the unit vector in the direction of interest, and that gives me the rate of change in this case, in the theta equals minus pi over 6 direction. So there was an extra step here, which was to, if I give you theta equals minus pi over 6, what's the unit vector that corresponds to that? Well, we go back to our right triangle trigonometry, right? We do cosine minus pi over 6, sine of minus pi over 6, which gives us that direction vector. So remember that interplay we had between the unit vector in the direction and the standard angle in the direction. That can come up here. Another example. So this one I have an arbitrary direction, and at the point 1, 2, find the rate of change. And so of course the answer is a function of a and b in this case. So that's kind of an interesting example. Like if you come up with that formula, then you can think about how the function changes in all kinds of different directions, all at once, instead of just thinking about one direction. I'm sorry, I seem to have brought one direction into this lecture again. I try not to do that. And then finally, yet another example, which I'll let you read. All right. And then this last example is kind of cute. Common test homework question I ask, sometimes test question. Find any directions, if any. Find directions, if any, in which f of this function has a rate of change of 1. So what we do is we leave the direction vector, symbolic, calculate the gradient at the point, and this gives me, I set the directional derivative equal to 1. That gives me 2a plus b equal to 1, but remember, it's a unit vector. So I still know a squared plus b squared equals to 1, so I have to solve this and that simultaneously. And when I do that, I get two directions. I get 0, 1, and also that. So there are two different directions in which the rate of change is 1 for this function. So I think that's pretty neat. And I think you guys will have no trouble at all calculating partial derivatives, but you need to do enough that you get bored with them. Let me just take the mystery out of it. You can use a formula sheet for test 2, but it is absolutely important for you to have the directional derivative formula on it. But not just that, you need to understand it, what it means geometrically, and I would encourage you to work through the problems in these sections. I mean, I'm sure it's so much fun to listen to me talk about them, but it's much better if you just work through a couple of them. But